Newly released image of 3I Atlas confirms it's not a comet.
The universe is vast beyond imagination, but every so often, something drifts into our small corner of space that reminds us how little we truly understand. This story begins with a flicker of light on a telescope monitor, a faint signature moving against the endless sea of stars. Astronomers marked it as a potential comet, an unremarkable interloper at first, until the data began to pour in. That was when everything changed. The object was given a name, 3I/ATLAS. The designation alone hinted at its strangeness. The I stands for interstellar, meaning it wasn't born in our solar system. It came from elsewhere, another star, another world, perhaps another time altogether. When the James Webb Space Telescope turned its powerful mirrors toward it, what it saw left scientists speechless. The Webb telescope was built to peer into the beginnings of the universe, to see light that had traveled for billions of years. But on this particular day, it was looking at something much closer, yet equally ancient. The observation was supposed to be routine, a quick scan to characterize the composition of an inbound comet. But the instant the spectral data came through, mission control at NASA's Goddard Space Flight Center went silent. Carbon dioxide levels in the gas cloud surrounding the object were off the charts. Normally, comets from our solar system are dominated by water vapor. They are, as textbooks call them, dirty snowballs, frozen time capsules from the early solar system. Yet 3I/ATLAS defied every model. The ratio of carbon dioxide to water wasn't just higher, it was 8-to-1. In all of recorded cometary science, nothing like it had ever been seen. To understand why that matters, you have to think about what keeps a comet together. Water ice vaporizes quickly when it nears the sun, forming the bright tails we see from Earth. Carbon dioxide, on the other hand, sublimates even faster and should have long since boiled away in the cold vacuum of space. For an object that has supposedly spent billions of years between the stars, the presence of so much CO2 was impossible. Yet there it was, venting into the darkness in quantities that no one could explain. The math said it shouldn't exist. The telescope said it did. Scientists tried to stay calm, but whispers spread quickly through the astronomical community. Could it be contamination? A calibration error? Every instrument was checked, every line of code verified. The results stood. Webb's detectors weren't lying. What it had found was real, and the implications were staggering. An interstellar object with chemical signatures so extreme it essentially broke our classification system. If our solar system's comets are the rule, 3I/ATLAS was the exception that refused to fit. Further analysis only deepened the mystery. A team from the Royal Belgian Institute for Space Astronomy ran simulations using cosmic ray flux models stretching back billions of years. They proposed that the outer layer of 3I/ATLAS had been transformed by galactic radiation, the same high-energy particles that sweep through the Milky Way and erode the surfaces of wandering bodies. Over time, those particles could penetrate up to 20 meters deep, altering the chemistry in ways we've never witnessed before. The crust of 3I/ATLAS, they said, was a record of the galaxy's own violence. 7 billion years of bombardment written into stone and ice. What Webb was detecting might not even represent the original material. It was like studying the burned shell of a book and trying to guess what stories were once written inside. But that theory raised a new question. If the outer layers had been cooked by radiation, what survived beneath? Could the interior still contain untouched material, pristine chemistry from a star system that existed before our sun was born? The possibility electrified researchers. If December's close approach allowed telescopes to probe deeper, they might glimpse the oldest unaltered matter ever observed. In a sense, 3I/ATLAS could be a messenger carrying a sample from a civilization of stars long extinct. Then came another surprise. On July 21st, 2025, Hubble captured an image of the comet that seemed to defy physics itself. A jet of material extended not away from the sun, but directly toward it. Every comet ever recorded in human history displays tails and jets that point away from our star, pushed outward by solar wind and radiation pressure. It's one of the most basic laws of cometary behavior. But there, unmistakably, was a 6,000-kilometer-long jet aimed sunward. At first, astronomers thought it must be a trick of perspective, a fluke of camera angle. Yet subsequent observations from Spain and Chile confirmed it from multiple viewpoints. Even Webb's own spectrograph saw it, gas streaming toward the very source of heat that should have been driving it away. No known physical model could fully explain it. Some speculated the jet might be caused by structural cracks that funneled gas in odd directions as the crust warmed unevenly. Others wondered whether magnetic interactions between ionized particles and the solar field could momentarily reverse the apparent flow. But none of the theories accounted for the strength and persistence of the feature. The jet simply should not exist, yet there it was, a blue spear of vapor reaching into the light. The strangeness didn't stop there. In late July, Chile's Very Large Telescope analyzed the comet's light and detected vaporized nickel in its coma. On its own, that was not shocking. Nickel often appears alongside iron in cometary spectra, but when astronomers looked for iron, they found none. Zero. In cosmic chemistry, nickel and iron are inseparable twins, born together in the hearts of dying stars. Finding one without the other is like finding smoke without fire. The data were double-checked, cross-verified, and confirmed independently by observatories in Hawaii and Spain. Nickel without iron, a combination that, until that moment, had no place in natural models of planet formation. Perhaps, some thought, billions of years of radiation had oxidized the iron into undetectable compounds, while nickel atoms remained free. That might explain the imbalance, but even the most generous simulations couldn't reproduce the exact ratios Webb was seeing. Something about 3I/ATLAS simply refused to obey the chemistry of any known system. It was as if it had formed in an environment where the rules themselves were different. Then, on November 1st, NASA's Jet Propulsion Laboratory confirmed the object was accelerating in ways gravity alone couldn't explain. Normally, comets experience small, non-gravitational pushes when jets of gas vent from their surfaces, essentially tiny rocket thrusters nudging the body along. But the acceleration observed in 3I/ATLAS was orders of magnitude higher than such effects could produce. According to calculations by Harvard astrophysicist Avi Loeb, for that much thrust to arise from natural outgassing, the comet would have had to lose nearly 15% of its mass, 5 billion tons of material. Such a massive release would create a vast, easily visible debris cloud. Yet telescopes saw no such cloud. The numbers didn't add up. Something else was pushing it. The parallels with Oumuamua, the first interstellar visitor discovered in 2017, were impossible to ignore. That object had also shown non-gravitational acceleration without visible outgassing. Back then, theories ranged from hydrogen ice sublimation to radiation pressure acting on an unusually flat shape. None were entirely satisfying. Now history seemed to be repeating itself. Was 3I/ATLAS driven by similar unknown physics, or by something even stranger? As October turned to November and the comet neared its closest point to the sun, the surprises multiplied. Solar observatories recorded a distinct blue glow enveloping the nucleus, an intense color rarely seen in natural comets. Most comets scatter sunlight toward the red end of the spectrum because their dust particles reflect longer wavelengths. But this one shone electric blue, brighter than models could account for. Some researchers suggested ionized carbon monoxide or cyanogen might explain it. Others pointed to the possibility of exotic organics, tholins, fluorescing under ultraviolet light after eons of cosmic radiation exposure. Yet the brightness and saturation of the color still seemed off the scale. It was as if the comet were wrapped in a luminous shroud of alien chemistry. When astronomers attempted to determine its age through orbital mechanics and galactic trajectory modeling, the results were breathtaking. Depending on which dataset you trust, 3I/ATLAS could be between 7 and 14 billion years old. That means it may have formed not only before our solar system, but perhaps before many of the stars we see in our night sky even existed. Its motion traced back to the Milky Way's thick disk, a population of ancient stars forged during the galaxy's youth. Whatever system gave birth to this object has long since died. Its planets shattered or consumed, its sun collapsed into silence. Yet one small fragment survived the apocalypse, drifting through interstellar night for eons until chance guided it here, to us. The comet's composition is a window into that lost era. Studying it is like holding a fossil from before Earth's creation. And that's why every space agency on Earth, NASA, ESA, JAXA, even private observatories, has coordinated to watch it during its December 2025 approach. At that time, 3I/ATLAS will pass about 1.8 astronomical units from Earth. close enough for detailed study but far enough to pose no threat. The Webb telescope has dedicated observation slots, Hubble's ultraviolet spectrograph is primed, and ground-based facilities from Chile to Hawaii are ready. 3 key questions drive their work. First, will a debris cloud appear, confirming the immense mass loss predicted by outgassing models? If not, the acceleration mystery deepens. Second, will the chemical composition shift as solar heat penetrates deeper layers? That would reveal whether the outer radiation-processed crust hides a more normal interior. Third, will the bizarre features, nickel without iron, the sunward jet, the blue glow, persist, fade, or change entirely? Each answer carries the potential to rewrite our understanding of how comets form and evolve across the galaxy. Yet beyond the technical details, a philosophical tension hums beneath the surface. Could it be natural, yet still extraordinary? Or are we glimpsing something that blurs the boundary between natural and engineered? When Avi Loeb published his analysis on the statistical clustering of anomalies, he didn't claim an artificial origin. He simply argued we cannot rule it out. The combination of extreme chemical ratios, directionally impossible jets, unexplained acceleration, and anomalous coloration occurring in a single object is statistically remarkable. Most scientists, of course, favor natural explanations. Random outliers exist, especially among interstellar objects formed under conditions we barely comprehend. But Loeb's caution struck a nerve. The debate reignited the same questions that surrounded Oumuamua years ago. How do we recognize the truly unprecedented when it stares us in the face? As the countdown to December 19th draws nearer, the anticipation builds. If the massive debris cloud appears, the mystery might resolve itself, an extreme but natural comet behaving in extreme ways. If it doesn't, the questions multiply. Each possibility leads deeper into the unknown. Either way, humanity wins knowledge. Meanwhile, Webb has revealed one more secret hidden in the numbers: the ratio of carbon-12 to carbon-13 isotopes within the gas. That fingerprint tells scientists about the environment in which the carbon atoms were formed. Astonishingly, the ratios in 3I/ATLAS match those found on Earth. Despite originating around a star system with vastly lower metallicity, possibly 10 billion years older, the carbon signature is nearly identical. That suggests that the fundamental chemistry of life, at least the carbon chemistry, is universal across time and space. The same kind of carbon that built our DNA was forged in stars long before ours and still travels the galaxy within objects like this one. It is, quite literally, the same material repurposed through cosmic recycling. We are, in every sense, connected to 3I/ATLAS. If carbon isotopes remain consistent across different galactic populations, then the building blocks of life could be everywhere. Interstellar comets like this might act as couriers, delivering organic precursors to young planetary systems. Hydrogen cyanide and cyanogen, both detected by Webb within the comet's coma, are molecules capable of forming amino acids, the seeds of biology. Perhaps such wanderers once visited our newborn solar system, seeding Earth with the chemistry that eventually led to us. In that way, 3I/ATLAS isn't just an alien visitor, it's family, returning home after a voyage of unimaginable length. Right now, as you listen to these words, the comet is visible in the pre-dawn skies, a faint, greenish blur through amateur telescopes. That glow comes from cyanogen gas, shimmering like a ghost. Astronomers across the world are tracking its every move, measuring, comparing, debating. December is close. When it arrives, all eyes will turn skyward. Data streams will pour down from orbit, and within hours, humanity will know more about its origins than ever before. Imagine the scene inside Mission Control on that morning. Screens glowing in dim light, scientists murmuring as numbers roll in. Somewhere in that torrent of data may lie the proof of theories that will redefine astrophysics, or the seeds of new mysteries that will haunt us for decades. Will the ratios change as the interior is exposed? Will the acceleration persist even as activity wanes? Will the sunward jet vanish or grow stronger? Every possibility is electrifying. If the 8:1 carbon dioxide ratio remains unchanged, it will mean that the entire nucleus, not just the surface, is built of material unlike any known cometary body. That would force astronomers to rethink how planets and minor bodies form in the earliest epochs of the galaxy. If the ratio shifts toward normal values, it could confirm the radiation-processed crust hypothesis. Either outcome reshapes our models. If the nickel signature continues to exist without iron, some entirely new kind of stellar chemistry must be responsible. perhaps remnants of supernovae from a metallicity regime we've never sampled. If iron finally appears as deeper layers sublimate, we'll have proof that cosmic radiation can fundamentally alter the outer layers of interstellar bodies. And if, by some miracle, the acceleration remains unexplained, if the object continues to move as though propelled by something unseen, then we may have to admit there are physical processes operating in space that we do not yet understand. The story of 3I/ATLAS is more than a catalog of anomalies. It's a reminder of how fragile our knowledge really is. Every discovery begins as confusion. Every revolution in science starts with data that doesn't fit. That's why missions like Webb exist. Not to confirm what we already know, but to expose what we don't. This interstellar traveler has already forced us to expand our imagination, to consider conditions billions of years older than the sun, to question the uniformity of chemistry itself. Soon, it will leave. After March 2026, when it passes near Jupiter's orbit, gravity will sling it back into the abyss, never to return. Our window is brief, a few months of observation after an eternity of silence. What we learn during this encounter will echo for generations. And perhaps, in some far-off future, another civilization around another star will detect an interstellar visitor from our system and wonder what secrets it carries. So what did the James Webb Telescope really find? It found a messenger from the dawn of the galaxy. It found carbon chemistry that shouldn't survive, metals that defy pairing, jets that contradict physics, acceleration without cause, and colors that no model predicts. It found a question mark carved in ice and dust, racing through our solar system at tens of kilometers per second. It found evidence that the universe still holds surprises far beyond our grasp. And maybe, just maybe, it found proof that the raw materials of life are written into the fabric of the cosmos, that the same carbon atoms drifting inside that ancient comet once danced inside the hearts of long-dead stars, the same kind that now reside in us. When we study 3I/ATLAS, we are studying our own origins. We are staring at a mirror made of frozen time. December 19th will arrive soon enough. The telescopes will watch, the data will come, and the truth, whatever it is, will reveal itself. Until then, we wait under the same sky that birthed that wandering fragment billions of years ago. Whether the answers show us natural extremes or something beyond imagination, one thing is certain: the universe is stranger, older, and far more wondrous than we can possibly comprehend. And 3I/ATLAS is its latest messenger, whispering secrets from the edge of time, daring us to listen. ChatGPT said, as the data streams continue to flood in, astronomers realize they are living through a moment that future generations will study in textbooks and documentaries. Every telescope on Earth and in orbit is pointed toward one single traveler, an icy fragment whose story began before our own planet even existed. 3I/ATLAS has become a symbol of cosmic connection, an echo of the distant past meeting the modern eyes of humankind. Yet even as measurements refine its composition and path, something about it keeps defying expectations. The more scientists understand, the more mysterious it becomes. Late-night teams at NASA's Goddard Space Flight Center and the European Space Operations Center start to notice faint fluctuations in the comet's spectral data. It isn't a glitch. Webb's instruments are too precise for that. The variations repeat every 71 minutes, as though something within the object pulses or rotates in a rhythmic cycle. A natural spin could explain part of it, but the modulation looks oddly structured, like a heartbeat that speeds and slows in deliberate patterns. Some whisper about internal venting cycles caused by deep cracks. Others point to rotation-induced jets, but no model fits the timing exactly. Even Webb's infrared sensors catch subtle heat signatures pulsing across the surface. Too regular to be random. Theories bloom like wildflowers. Could a deeply buried pocket of volatile material be venting in intervals? Could internal stresses from cosmic ray damage create repeating fractures that reseal themselves in the cold? Or could something within the nucleus, perhaps a trapped magnetic domain, be interacting with the sun's field in a way we've never observed? It's speculation layered on speculation, but it shows one thing clearly. 3I/ATLAS is not a simple rock. It's dynamic, restless, alive in its own frozen way. Meanwhile, the object's motion continues to puzzle physicists. Its trajectory bends slightly more than expected, hinting that the mysterious acceleration isn't a one-time event, but an ongoing influence. Precise radar echoes from the Goldstone Observatory reveal micro-oscillations in its path, as though the force pushing it changes direction every few days. Gravity can't do that, nor can sunlight pressure alone. If outgassing were responsible, the pattern would align with its rotation period, but it doesn't. It follows no known rhythm. To some, this looks like chaos. To others, it's a coded order hidden beneath noise. The debate grows louder as December approaches. In the media, 3I/ATLAS becomes more than an astronomical event. It's a cultural phenomenon. Headlines call it the alien comet, though no scientist has made such a claim. People stay up until dawn scanning the skies, hoping to glimpse it through binoculars, whispering that it glows brighter each night. Internet forums overflow with theories. Some insist it's a natural relic of an ancient system. Others dream it could be something built, perhaps long ago, by civilizations we'll never meet. NASA's official statements remain cautious, emphasizing observation and patience, but even the most stoic researchers can't deny the thrill of mystery. Then, a faint radio anomaly catches attention. During one of Webb's high-resolution scans, a background frequency spike appears exactly at the object's coordinates. It's weak, buried in noise, and could easily be an artifact from cosmic interference or internal electronics. Yet it repeats 3 times over 40 minutes before fading. Engineers check every system. Nothing local matches the pattern. No known spacecraft or satellite aligns with that position. It's probably coincidence, they say, but the data is saved and circulated quietly among teams for independent verification. Even a false positive must be explored. In science, every oddity is a clue. Night after night, as the comet edges closer to the sun, telescopes record its transformation. The once solid core begins to fracture, sending plumes of gas and dust spiraling outward. But instead of forming a chaotic cloud, the material organizes into a faint ring, orbiting the nucleus like a halo. Spectrographs show the ring's composition shifting as it rotates. Nickel vapor cooling into micron-sized grains that shimmer blue under ultraviolet light. It's beautiful and eerie, a cosmic dance choreographed by forces no one fully understands. The sight leaves observers silent at their screens, aware they are watching something that will be discussed for decades. By mid-December, 3I/ATLAS has become the brightest interstellar object ever recorded from Earth. The blue aura now stretches millions of kilometers, reflecting sunlight with a brilliance rivaling Venus in the pre-dawn sky. Children watch it before school, couples record it through telescopes, and poets write about the ancient visitor returning home. Humanity, for a brief moment, is united by wonder. In control rooms and observatories, scientists work without sleep, balancing awe with precision. They know that in just a few weeks, it will be gone forever. On December 19th, as the comet reaches perihelion, instruments capture the most detailed images yet. The nucleus glows like a sapphire ember, veiled in cascading jets that weave in patterns reminiscent of auroras. The sunward jet still burns fiercely, but now 2 more emerge at right angles, forming a cross-shaped structure, its geometry written in vapor. A cosmic compass etched in light. For a fleeting hour, radio telescopes detect an electromagnetic echo unlike any natural plasma fluctuation ever seen, a resonance pattern that mirrors the comet's rotational frequency. Then, as quickly as it appeared, it vanishes. When the data finally settles and the comet begins to fade, Earth is left in silence and wonder. No one knows exactly what they've witnessed. Some say it's the most complex natural object ever recorded. Others believe it hints at unknown physics beyond current theory. But everyone agrees on one thing. 3I/ATLAS has changed the way we look at the universe. It reminded us that even in an age of advanced telescopes and deep space probes, the cosmos can still surprise us in ways that feel almost supernatural. And as the comet recedes into darkness, heading back toward interstellar space, its story becomes legend. A frozen traveler carrying secrets from before time, whispering that the universe is alive with mystery, waiting for us to keep looking.